I would like to thank the organizers for giving me the opportunity to speak in this event. So the title of my talk is The Linearly Edge Reinforced Random Walk on Z. I'll call it ERRW. And so this is based on work in progress with Abhishek Dar and Riddhi Pratim Basu from ICTS. And we also had useful discussions with Gadi Cosmo from Weizmann Institute of Science. So let me get started. So I'll begin by describing the model. So the edge reinforced random walk is defined on any locally finite graph. But in this talk, I'll restrict my attention to the graph Z. Let's consider the graph Z. So on each edge of the graph, I'll consider an initial weight AE. And so AE of 0 is the weight at time 0. So for simplicity, I'm going to take the initial edge weights to be constant A, where A is any positive real number. Now, after fixing an A, I'll run a nearest neighbor random walk Xn on Z as follows. So at time n equal to 0, I start at 0. And if I'm at a particular vertex X at time n, then at time n plus 1, I'm going to move to the right edge with a probability proportional to the weight on the right edge, and to the left edge with a probability proportional to the weight on the left edge. And after traversing the edge, I'm going to increment the weight on that edge by 1. So I'll denote by Xn the position of the walk at time n, and AE of n the weight on the edge at time n. So let's look at a small example. So this alpha xn plus 1 is the probability of jumping to the right vertex at time n plus 1. The probability of jumping to the left vertex is then given by 1 minus this quantity. So here I'm considering initial weights A equal to 0. So I start at 0, and because the initial weights are all equal, there is an equal probability of jumping to the right or to the left. And let's say I jump to the left, then I increment the weight on this edge by 1. So now the probability of jumping to the right in the next step is going to be given by 2/3, and the probability of jumping to the left edge is probability of jumping to the left vertex is given by 1/3. So this is the model. So what does this? What behavior does this walk model? So suppose you are new to a city, and so initially you explore places randomly, and as time passes, you are more likely to visit streets that you have visited already. So this is the behavior, the edge reinforced random walk models. So we can see that as the walk evolves, the environment, it influences the environment, and the environment keeps evolving dynamically. So by the environment, I mean the transition probabilities alpha x. So let's look at some sample trajectories of the edge reinforced random walk and compare it with the simple random walk. So if A is small, then the reinforcement is going to be very strong. And if A is large, then the reinforcement is going to be weaker. And in the simple random walk, there is no reinforcement. There is equal probability of jumping to the left or to the right at any time. So if I look at A equal to 0.1, then we see that the walk is stuck on 2 edges. So this is the time axis, and this is the position. And we see that for A equal to 0.1, here it's stuck on 2 edges, and 2 edges here, and just 1 edge here. For A equal to 10, the walk visits more sites, And for the simple random, so here it's like 40 sites, and for the simple random walk, we see that the range is more than 100 sites up to time 4000. So now the question is, we know that the simple random walk is recurrent, but the average return time to 0 is going to be infinite. So we ask, is the edge reinforced random walk recurrent? And if it is, what is the expected return time? So now one might think that because the simple random walk, which has no reinforcement, is already recurrent, probably it is obvious that the edge reinforced random walk is also recurrent. But there is a slight issue here. Suppose the walk moves here and gets stuck on an edge which is away from the origin. So in that case, we need to show that even if the reinforcement is strong, the walk doesn't get stuck at some edge which is away from the origin. And then what's the expected return time? Because there is reinforcement, is the expected return time going to be finite, contrary to the simple random walk? And the answers to these questions are already known. So the edge reinforced random walk, in fact, turns out to be recurrent. So and in fact, it visits all the vertices infinitely often with probability 1. And this is true for any positive value of A. So this picture is a bit misleading. So it does visit all the sites, but it's just going to take very long. And so is the expected return time going to be finite? And it turns out that even though there is reinforcement, the expected return time is still infinity for any positive value of A, even if the reinforcement is strong. So the edge reinforced random walk is very difficult to analyze because it has an environment which keeps evolving dynamically, and there is a coupling between the walk and the environment. So it's not so easy to analyze. So, but fortunately, there is a connection to the model called the random walk in a random environment. So in fact, this equivalence says that the edge reinforced random walk is equivalent to a random walk in some random environment by law. So let me describe what this random walk in random environment is. So so the environment omega is defined as follows. At each vertex, I have a random variable omega taking values in 0, 1. So these are the probabilities of jumping to the right of the vertex x. And these omega x's are independent. And these omega x's are distributed as follows. For x greater than 0, it's going to be distributed as beta of a by 2, a plus 1 by 2. And for x equal to 0, this is going to be a by 2, beta a by 2, a by 2. And for x less than 0, this is going to be beta a plus 1 by 2, a by 2. And I'll call uppercase omega the space of environments, and I'll denote by P the distribution on the space of environments omega. And this is going to be, because these omega x's are independent, this probability distribution is a product of these beta measures. Now, so I'll describe what a quenched law of the environment is. So I fix an omega in the space of environments, and a walk under the quenched law is given by, so I have a fixed, I have picked an environment according to these probabilities. So I have different transition probabilities at each vertex, and I perform a random walk under this environment. So the probability of jumping to a vertex x plus 1, starting from if I'm at a vertex x, the probability of jumping to x plus 1 at time n plus 1 is going to be omega x. So these are fixed random variables. And the law of the edge reinforced random walk is the same as the law of the annealed random walk in random environment. So what this means is as follows, is the following. So I suppose I consider an event and look at the probability of this event under the law of the edge-reinforced random walk, which is this P, and then I fix an environment omega and look at the probability of that event under this environment omega, and I do this for each omega in the space of environments, and I take the expectation of this probability. So for each omega we are going to get a different value here, and I'm going to take an average of these values and according to the measure P. So it turns out that these two laws are equal. So this is the so I have an environment and I average over the environment. So this is called the Anil law of the random walk in random environment, and this is the law of the edge reinforced random walk, and they turn out to be equal. And the random walk in random environment is a bit more easier to analyze because for a fixed environment, the walk is going to be a Markov chain. So the probability of transitioning from one side to another just depends on the fixed environment at that site. So this is Markovian, and we have a mixture of Markov chains. So this is much simpler to analyze. And what we are interested in is the limiting distribution of the position of the walk at time as n goes to infinity. So this is denoted by, so this is a limit of probability of xn equal to some value. So let's fix some a greater than 0, and I'll call by pi n omega of x the probability that the walk is at x at time n under the environment omega. Now, so for almost every omega, we can show that there is an invariant distribution pi omega of x, and which satisfies this detailed balance condition. So if we want to look at the, so because of periodicity, the walk can be only at even sites at even times and odd sites at odd times. So however, if we take the average of these two distributions, then this will converge to pi omega x, and this is going to be non-degenerate. So this is special to this particular, to the environment we are considering. Suppose we also have that the expectation of pi omega x is finite, then we can show that we can interchange these two limits. So this is the law of the edge reinforced random walk, and this is the law of the random walk in the random environment. And if we want to find the limiting distribution, we can change, we can interchange the expectation and the limit, and so this is what we want to analyze. So we we can just study this pi omega x to understand the limiting distribution of the position. Now the result we have is as follows. So we have an asymptotic estimate for the limiting distribution of the position, and suppose we fix a greater than 0, then for all epsilon greater than 0, I can find some extra such that, so this is small x, for x greater than x star, I have this inequality. So this gives a tight exponential bound for the limiting distribution when x is large. So we can make this error very small by choosing x to be very large. Now this L star has a simple form which is given by this formula, and yeah. So this is what log. So this is what pi of x looks on a linear log scale. So it's going to look linear. So the result follows from analyzing, from using some large deviation calculation on these environments. Now, if we look at the limiting, so if we look at the first return time distribution of the random walk, so this is this looks like n to the minus 1/2, which, sorry, n to the minus 3/2, which is similar to the which is similar to that for simple random walk. And so these are the limiting distributions for different values of x for different values of n. For different values of a, and we see that for any a greater than 0, the probability that the first return time is n scales as n to the minus 3 half. So this is our second result, and yeah, I'll skip this part. Thank you.